What's your class number? 431, 431? Okay. I just want to see how many students are here.
Well, the class actually doesn't start until 4:30.
Oh, okay.
So some of them may have a conflict. Okay. We'll get started. Well, why don't we get started? Good afternoon, everyone. Thank you for coming. I'm Kevin Jaffe, and it's my absolute great pleasure to introduce a colleague, Jim Kurose. Jim is coming to us most immediately as the Assistant Director at the NSF, where he's then head of CISE, which is near and dear to all of our hearts. But Jim is far more than just the Director of CISE. Prior to that, he's been a Dean, he's been a Department Chair, and before all of that, he was just a distinguished networking researcher.
And still is.
And still is, right. As he assures me, he gets time to think about some technical stuff. On the research side, Jim has won just about every major award in networking. He has received the Infocom Achievement Award, the SIGCOM Lifetime Achievement Award, and there's still plenty of room left in your lifetime.
Look at all these gray hairs.
Yeah. As well as the SIGCOM Test of Time Award and the IEEE C.S. Taylor Booth Education Medal. And as is interest to many of the people here, he's also the author of the textbook that we currently happen to use, and that nasty homework problem that you assigned that has the square root L in it. That comes courtesy of Jim. So, Jim today is going to give us a talk about his work at the NSF, so take it away, Jim.
Great, thanks Kevin. So, hi everyone. Actually, how many people here are from Kevin's networking class? All right. So for those of you who want, we can come down here at the whiteboard and I'll walk you through at least the first half of the solution to the homework problem that he says is sort of puzzling you, okay, about the square root of the loss rate, okay? We can work that afterwards interactively. So so it's really nice to be here and hi to, where's the camera? So hi to folks who are here from Duke and NC State also, and here, well, hi right in person, and also those who are remotely. So it's really nice to be here. I've been, I think, to each of the universities now multiple times, and so it's always great to come back. I'm going to talk today about things going on at the National Science Foundation, and in particular in the CISE, Computer and Information Science and Engineering Directorate. So as much as I'd love to talk to you about networking research, I'm going to talk to you more about computer science sort of broadly writ and things going on at the National Science Foundation. So as Kevin mentioned, I've been a professor for a long, long time. I've only worked at NSF for 2 years. So I've taught long enough to know that the last thing anybody here wants is for me to get up here and start and talk, and not stop, and then say thank you and walk away. So let's try to make this interactive. I'm going to try to put on my best professor hat and remind myself to stop and see if there are comments and questions as we're going along, okay? So if there's anything you want to say anytime, just shout it out, raise your hand, anything like that. So here's what I'd like to talk about. I first want to talk about the CISE, the CISE, our field, right? So I used to always say computer science, now I have to say computer and information science and engineering, CISE. I want to talk about that from sort of a national viewpoint. I want to then tell you what's going on at the National Science Foundation in CISE programs, and then really talk a little bit about the future and some of the challenges that I see. Okay, so if you were to ask a random faculty member at any of the 3 universities here, what's NSF about? They will tell you, oh, it's about funding my research, right? And so that's absolutely true, right? Pushing forward the progress of science. But there's a larger context also, and this is actually from the founding of the National Science Foundation. in addition to pushing forward and doing funding basic research in science to advance the national health, prosperity, and welfare to secure the national defense. And so you see this sort of national need and the importance of what we're doing at the National Science Foundation, in addition to funding basic research. So, when I started 2 years ago, or even a year ago, there were 4 sort of national initiatives that actually got started by the White House. So there was a big data initiative. Cybersecurity has always been important. If you were to look at the NSF budget over time, you'd see that funding for cybersecurity always goes up. It never goes down. The National Robotics Initiative, I talked to a number of folks here who were actually instrumental in helping get that started and understanding the brain. And so, imagine how cool it is to, go to Washington and want to do some service for your discipline and find, hear the White House and other folks telling, okay, these are nationally important areas. And so that's always amazing. So within the last year plus a little bit, there have actually been 4 additional national initiatives that have been announced. And when I say national, I mean sort of all of government. So this is the government agencies coming together and often led by the Office of Science and Technology Policy, saying here are things that are really important to the nation as a whole. So the National Strategic Computing Initiative, this is high performance computing. This is all about not just big iron, but hardware. Yes, the big iron, but also software and data and networking and security. Smart and connected communities, that's what we call it at the NSF, the buzzword smart cities within the White House. Computer science for all. How many people here have heard of computer science for all? Oh, okay, not too many. All right, well, I'm going to tell you a little bit about that, and then an advanced wireless research initiative that I'll tell you a little bit about also. So even just within the past year, we find ourselves in computer science, in the middle of these 7 official national initiatives in cybersecurity being always important. So, when I was at the University of Massachusetts, I was always fond of telling our chancellor that computer science was at the center of a modern 21st century university, and now I decided it's actually at the center of all the things that are happening in Washington also. So, national importance. Okay. So before I get on and talk a little bit more about sort of what's going on at the NSF, I want to show you one of my favorite graphics. And I'm going to ask again, how many people have heard of the tire tracks diagram? 1. Okay. Wow. Okay. So let me tell you, this is this diagram that I'm going to show you. I use it. One of the things I have to do in my job, and I enjoy it, is I talk to folks on the Hill, so whether they're staffers or legislators or senators, about the importance of computer science and what it means for the country. And I'm going to show you a graphic that actually has its origins right here at the University of North Carolina, because I'm going to show you an updated graphic that comes from the original Brooks-Sutherland report. So Fred Brooks, who I guess retired from here fairly recently, the concept for this diagram came from the 2 of them. And I have found it sort of the most effective, you can roll it out in front of anybody and you can tell a great story. So if you're a fan of graphics and how graphics and visually how you can tell stories, I hope you're really going to like this. So this is all really about what computer science, what cyber infrastructure, information technologies means to us as a country. And you see some statistics here about the impact that it's had. So let me show you what this diagram is. And we always tell our students, whenever you put up anything graphic, say what the X and Y axes are and things like this. So let me pick networking, which is my research area, and show you what's going on here. So you see time going up like this, and you see a bunch of colored lines, right? This red colored line, this is when research and networking actually started in a university context. So this was like way before a lot of you, I can tell just by your age, were born, and it was way before the internet came around or anything like that, right? So here's research in universities, and that's sort of powered by federal funding going on in networking here. Here's when it started off in industry here. So this is this blue line here. And when you see this narrow green line, this is when it became a $1 billion industry. And when it gets fat, this is when it became a $10 billion industry. And actually, these lines are not the most interesting thing here. What's really interesting are these arrows that go back and forth like this. And each of these arrows represents a documented case of an idea, a person, a piece of software, something that moved back and forth between academia and industry, and back into academia and industry, and back and forth, and then into products. And this sort of close collaboration between what happens in academia, what happens in industry, and then the growth of these multi-billion-dollar industries is sort of part of the story, part of our narrative as computer scientists. And I don't know, I find this is sort of a really uniquely American, sort of US way of industry and academia interacting with each other, and I think a really very powerful story. And this has been repeated, so you see software here and networking here, and the full Brooke Sutherland report, actually this is actually updated this is a 2013 National Academy of Science report. You don't have to read this, right? This just says, look, AI and robotics, graphics, databases, distributed systems, software architecture, digital communications, all of them have this story again and again and again, from one area of computer science to another, and you see all the companies up there that we all know and love very well. So when we talk about national impact, you saw that mission of the National Science Foundation. When I talk in DC to funders and to other branches of government, this is part of the story that I tell about the impact that computer science has on the country. So you might notice that timeline stops at 2010, okay? And for those of us in the networking field, it's always great to say, oh, we gave you the internet, right? And we would say that, and around 2000, that sort of started to wear off, right? You couldn't just say, oh, networking is a great area to be working, we gave you the internet. People would say, oh, what have you done for me recently, right? Because that's old stuff, right? And so this stops at 2010, so I just wanted to address for computer science this question, what have you done for me recently, right? And rather than do that, let me just say that this is a nice infographic that I pulled from McKinsey, which talks about the 12 most disruptive technologies by 2025. And when you look at them, mobile internet, automation of knowledge work, Internet of Things, cloud, robotics, autonomous systems, 3D printing, energy, next generation genomics, you might think that all of these are about, oh, this must be sort of IT or computing related, but actually this is across all areas of technology. And so again, I think that the impact that our field is going to have going into the future, well, I think it's sort of self-evident here that there's just so many areas in which we're going to contribute. So for those of you who are students, and actually those of you who are professors also, maybe you've seen some of these statistics. So when you look across all of science, technology, engineering, and math and say where are the jobs going to be in the 2014-2024 timeframe, you can see the computer occupations here, 55%, the rest of engineering 26%, and then life sciences, physical sciences, and social sciences. And so when it comes to jobs, and jobs are important, I'm sure you're all seeing something that looks like this here, right? So you're seeing, this is plotting the number of newly declared undergraduate computer science, computer engineering majors. This came from what's called the Talby survey. And so you see sort of this incredible uptake here. So I imagine at all three of your campuses, you're seeing this kind of explosion in student interest. And actually, is there anybody from the dean's office here? No, that's too bad. I have a slide later on that I put in, I was hoping there'd be somebody from the dean's office here, so I'll tell you when the dean's slide comes up, and then you can, is this being recorded? So you can, I'll just watch your watch and just tell the dean to just fast forward to, I don't know, 35 minutes in and watch what's there. But it's actually talking about this explosion in the interest of majors in computer science. Okay, and then finally, within government, there are sort of these all-of-government strategic plans for federal research and development. And so within the last year, we've had 3 of these that have been put forward, one on privacy, one on cybersecurity, and most recently, the president announced at the Pittsburgh Frontiers Conference about a month ago, the AI R&D strategic plan. And so, again, I just think one last time sort of talking about the centrality of computer science to all these things that are happening around the country. Okay, so anyway, this is the high-level message that I want to leave you with. In some ways, people of my and Kevin's and some of you other vintage, sometimes I feel like Forrest Gump, right? Because I went into computer science before there was even a computer science major where I was studying, right? I just learned how to program, and then, okay, I went to get a master's degree in computer science and sort of fell in love with it. But, you know, we sort of fell in love with a field that was really at its very, I like to think, you know, at its beginnings, and then it's become something of such central importance, really to the whole country. And so a very exciting time to be here. Okay, so that's it just for the national imperative, sort of the big picture and things like that. I want to tell you a little bit about NSF programmatics, but actually let me stop for a second, since I've talked for 10 minutes, and I should always stop myself. Any comments or questions about anything you've seen so far? Okay. All right, I'm going to go, but next time when I stop, somebody better have a comment or a question. Otherwise, I may have to beg for a question or something untoward like that. Okay, let me tell you a little bit about programmatics at NSF. So I apologize, I have an org chart here, and it's not so much the org. I just want to tell you sort of how the National Science Foundation, the CISE Directorate, is structured. So we have a division of advanced cyber infrastructure. So again, I mentioned before the National Strategic Computing Initiative. This is actually a division within CISE right now, but it serves all of science and engineering. So physics and math and chemistry and engineering and biology and education, social behavioral and economic sciences. So this division provides high performance computing, networking, security, software, a lot of research and infrastructure programs that serve the whole foundation. We have a division of computing and communication foundation, so this is where theory goes. Algorithms, communication and information theory, and hardware and software foundations. For those of us in networking, this is sort of our home division in computer and network systems. And then finally, and this is honestly the area where we've seen the most growth over the last couple of years, information and intelligence systems. So this is where robust intelligence is, machine learning, CyberHuman Systems, robotics, activities like that. Okay, so that's sort of who we are and how we divide ourselves up. And let me show you one more infographic here, because this is something that people often find interesting. So the budget that we have for the CISE Directorate, well, we don't know what our 2016 budget is yet, so we're in a continuing resolution there. But last year, our budget was $933 million. 8,000 proposals coming in, 1,800 awarded, and that orange thing up there, a 23% success rate. So let me comment on that a little bit. So That doesn't count like workshop proposals, things called eagers that are just generally funded and have a very high hit rate, but that's the average over everything else that comes into CISE. Some are higher, so we put a lot of emphasis on career awards, the CISE Research Initiation Initiative, CRII. I know folks here have been funded over that. We put a lot of emphasis on junior faculty and sort of early career activities. So the success rates there are actually higher than this, and in other areas, obviously, they're lower than this. I talked to a number of people about these kinds of things today. 7,300 researchers, think faculty members, 6,400 graduate students, and a lot of undergraduates through research experience for undergraduate programs, for example. So the people are always very important. And then finally, let me just say a word about budget, because we should all know about the budget in Washington, and I think almost everybody I've talked to today asked me about the budget in Washington, and I'm happy to talk about that if other people want to talk about that. But this is sort of the story of what life has been like in DC and federal funding for basic research since 2010 at the National Science Foundation. So this is for the CISE Directorate, but the NSF budget tells pretty much the same story if you look at it as a whole. So, I like to be an optimist. I say, okay, modest growth. So you can see it's 1%, 2%, 0.028% 1 year, and that these modest increases are sort of shared across the different divisions that we talked about. So that's sort of the budget reality of life in DC over the last 6 or 7 years. And I have one other statistic that I want to show you, and that's this number down here, 82%. So what this graphic is showing is, think of all of the federal research money for basic research. So every agency in the federal government says, this is how much we spend on basic research in each of these different areas. In computer science, 82% of the basic research from the federal government in computer science actually comes through the National Science Foundation, right? That's a really, really big number, right? And one of my goals as the CISE assistant director is really, to make the pie bigger, absolutely, right? So we want to increase the amount of funding, but we also want to diversify. And so there are a number of ways to do that, one of which in particular that I'll talk about a little bit later is to form partnerships with other federal agencies and do joint funding of research activities with other agencies like the National Institute of Health, for instance, or the Department of Transportation or the Department of Defense. Okay? All right, so I want to, there's a story behind this slide, but before I go on, I want to give you, this is going to be a one-slide overview of all of computer science. I'll tell you the story first behind this. So when I got to NSF, we go on a retreat every year. All the assistant directors go on a retreat, and the director said to all of us, he said, okay, we want to have a lot of discussion, so I don't want to see a lot of slides, but I want each of the assistant directors to talk about what the past has been like and where the field is going into the future and what's important, and I want you to do it in one slide. So I'm going to show you my one-slide overview of computer science and where it's been and where it's going. You can tell me if you sort of get it and like it. But before I do that, any comments on the data that you've seen? Again, I just sort of wanted to present sort of a holistic picture of what's going on federally, the amount of funding, where computer science sits, and the importance of computer science. So before I go on and start talking about some technical areas, any comments or questions? Oh, thank you. Yes.
National Institutes of Health obviously funds a lot of research involving computers.
Right.
How do you distinguish? You said theoretical computer.
Oh, I said basic computer science. Right. So that's a great question. So each agency defines for itself how it declares where it's putting its money, or how it's making its investments. So let me say that the National Institute of Health says that that 0% of their investments go into basic research in computer science. Now, of course, they have programs like BD2K that are really, they have a lot. Those are that has to do with big data and its use in healthcare and NIH type of settings, and there's a lot of funding that goes into that. My guess is that NIH, their mission is not to fund basic research in computer science, and so they will say, well, that's more applied computer science, and it's adaptation of existing machine learning techniques and data mining and applying that to the health. So that doesn't actually show up here. If you're interested in actually the NIH and the Department of Defense, which actually is another part of this 18% here, the Tolby survey that I mentioned before actually breaks down, rather than saying what federal agencies declare, it looks at the individual departments that sort of contribute to the Tolby survey and say, where does that funding come from? And you'll see the NIH showing up there, obviously much more significantly. So this is just showing, so you should take that number 82% with a grain of salt, but this is sort of what the federal government says, and it's what agencies declare, so I wanted to show it to folks. Thank you. Yes?
So you showed in a graphic, a very nice graphic, how the growth and the boom in computer science demand, there was this big bubble that happened in the late 1990s,
right.
Went away in the early 2000s, and then another one that we're in the beginning of now, where we're seeing explosive growth.
Right.
What's different to me is the funding situation feels very different in this one. I mean, you've already passed that one, then it fell to that one, having been through both of them, right? It seems to me, there was a lot more opportunities for funding new research in that era. Here, it's a lot tighter.
Yeah,
but the demand for our majors hasn't increased at all.
Okay, so that's a great comment. Actually, I want to come back to that. So let me just sort of reiterate what you said and then make a couple comments on, because I want to come back to that later, because I think the growth of the field combined with that flat budget exactly contributes to exactly what you're feeling. So for those of you who are off campus here, the comment is that, okay, we've been through these waves of explosive growth at least once before, and actually once before here if you go back even further, and the feeling is that there was more, now from a research funding standpoint, that, for instance, success rates were higher here or higher back here, and that's absolutely true. So if you were to go back to the wave even before here, sort of back in the 1980s, you'd see that success rates were close to 30% back then, and you saw now they're 23, and in some programs they're lower than that. So it's absolutely a fact that funding rates have gone down. I mean, that's true across all of the National Science Foundation. One of the things, and this is what I'll talk about later, so I'll just give you a preview of this. One of the things that we're seeing, partially in response to this, right? There are clearly a lot more students, but I think there's more interest. I mean, I think computer science is becoming increasingly an outward-facing discipline. We're making more connections with other disciplines, more research connections with other disciplines. And so what you see is, you see universities making more investments in computer science faculty positions. I'll give you one statistic, which to me, this is something that keeps me up at night. So between November 2014 and November 2015, if you look at that year and compare it to the year before, the number of tenure-track positions in four-year colleges plus Research One universities went up 46% in 1 year, right? And those are tenure-track positions, right? So that's universities, you're all in university here, right? And it's definitely the case that faculty slots, tenure-track faculty positions, are the coin of the realm. And when an administration decides to make an investment in a tenure-track faculty slot, that means they're in it for the long term, right? So I think both sort of the increasing centrality of computer science as well as the student demand, we're seeing this. We're just beginning to see, I think, the increase in tenure track faculty slots, as evidenced by that one statistic. And so that actually comes from a guy named Craig Wills at WPI. He publishes something every November, so pretty soon we'll have the 2015 to 2016 report out. But I predict we'll see, again, pretty high hiring. Again, that's my sense. And so one thing that keeps me up at night are those flat budgets, and we're just beginning to see the increase in the number of faculty positions. So I'll come back and comment on that, but I think your sense is absolutely right, and I think it sort of makes that 82%, and it makes collaborations with industry, and it makes collaboration with other federal agencies even more important. So yeah. Okay, yes, great.
Just to counter that point, I was in an engineering panel, and the engineering program manager looked at me and said, "We are engineering, we're not as well funded as you computer scientists, so please use high standards." So I'm just curious, how do we manage to get more money than them?
Okay, well, so the comment, which I'll simply repeat since you were saying it, has to do with a comment from engineering that you were in a panel in engineering and the engineer said, we're not as well funded as computer science and therefore have higher standards or something like that? All right.
Saying that to me, I forget what.
So it actually is the case. If you were to look all across the National Science Foundation, the directorate that generally has the lowest success rates is the engineering directorate, right? And I mean, that's sort of just a fact. How did we, computer science, how did we, computer science, get to be, well, I don't know, we're at 23%, which doesn't strike me as particularly high. It used to be higher. There was a very significant, the last really big significant infusion of funding into CISE happened in the early 2000s. People here maybe remember the ITR program that happened, right? And that was a very focused investment primarily in computer science, and I think that had a huge effect on what's happened with computer science funding. Yes, oh great.
My own area is human task model. Where would that fall under this chart that you had?
Okay.
Information intelligence system?
Yep. So
it's kind of not, it's not quite brain, it's brain and body.
Right, so
CyberHuman system.
Right, so that kind of activity would fall over here in CyberHuman Systems. Next, I want to talk about that in just a second. Okay, there was one other question, so it's great. I'm really happy not to talk and just to have it be a conversation. Yes?
I was just curious about, one thing that I've gotten before from people in other countries is that the funding increments that computer scientists get here are relatively small, right? So most of us have multiple active grants, and
right.
This chart, it's, the average person, I'm assuming, has multiple things. Like, is it a good idea or a bad idea to give out money in bigger parcels, for instance, and lower the reviewing overhead, lower the funding application cycle, and spend more time doing work?
Yeah.
Do you have any thoughts about this?
Okay, so that's a really, really good question. The question is, the pros and cons over smaller number of larger grants versus a larger number of smaller grants. So let me tell you, the engineering directorate, for example, even though it's got some of the lowest funding rates just in sort of the core programs, it also, it has there's incredible proposal pressure there, right? And so the model there for those tend to be a larger number of smaller grants, right? So I think what we in CISE, and really all the directorates do, is you want to maintain a balance of these kinds of things, right? Because there are the 3-year, small, medium, and large grants, but there are also sort of center scale grants. So I'm not really going to talk here about expedition programs, but something that, and for instance, I was a PI on an engineering research center where it's, it's $5 million a year, and it's 10 years that you have to get renewed, but assuming you're doing good stuff, you get, that lasts for 10 years. It is really, if you really, really, really want to move the needle big time in an area, I'm personally a big fan of 5-year grants, and in some cases 10-year grants. So the expeditions program that we run within CISE is they're about half the size of ERCs if they run for 10 years. But it takes that sustained period of time of, especially in interdisciplinary areas, of people collaborating with each other in order to, push forward that frontier. So, I understand I've been a PI way longer than I've been an NSFer, right? And so if I have a 3-year grant, sometimes in the first year, I've got to get I got to get a good student. And, so the first year is, I'm not running on all cylinders, and then I'm running on all cylinders and doing great things. And then I'm like, oh my God, the grant ends in a year. So I'm starting to think, I got to write another proposal. And you can get a no-cost extension, so maybe it lasts 4 years. But I'll contrast that with having been a PI again on an ERC, where from years 2 through 7, you've got like this big group of people who know each other, understand each other's vocabularies and ontologies, and are all working on the same, problems, and interrelated set of problems. And you can really push things forward there. So personally, I think we need to have this portfolio, and I really appreciate the larger scale and longer term grants, but we need the smaller ones too. So it's really that mix that we've got to have. But it's a really great point. Okay, all right, so let me tell you, all right, so this is my one slide. So some of you are undergrads if you're in, your course is an undergrad course, right? Okay, so some of you are undergrads. So this is my one slide summary of what computer science is all about, so you can tell me how it works out. And of course, in one slide, because that's all we were allowed, I had to use overlays and a whole bunch of animations and things like that. So here it comes. Okay, so okay, we have our core. We have, in a sense, the foundations. I never like to use the word core, because if you're not in the core, then you feel like you're not in the core, and then that's a bad thing. So okay, we have our foundations, and these are sort of the traditional disciplinary areas that you've probably all taken courses in. Okay, so. Here's thinking forward, thinking where we've been and thinking forward, here's the thought experiment I want you to do. Project yourself forward to 2030, okay? And imagine what computer science looks like 15 years from now, right? And then turn around and say, okay, what were the big changes between 2015 or 2016 and 2030? What do your kids, what do your grandkids, how is computing different for them 15 years in the future, sort of looking back, what's changed? And so I want to give you my candidates of 4 areas that I think will have changed pretty profoundly. And this is probably the one I'm the least confident in. But, so for time immemorial, when you talk about computing, it's been electrical, it's been about CMOS. But there are activities in quantum computing. In CISE, we fund an expeditions at Caltech on molecular computing, optical, nano. And so the notion of what it means to physically compute, you might think about, okay, sort of on beyond electrical, right? So there are these other modes of thinking. Quantum computing is something that's at one of the pieces that's at the center of the National Strategic Computing Initiative. So that's the changing physicalness of computing. Okay, this is the one I'm most sure about. Ask your mother or your father, what's a computer, right? Or what is when you think about computing, what physicalness do you think about? And they will say, maybe a desktop, one of those, I think there's one in here, or a laptop, or maybe a phone if they're sort of forward thinking, or a pizza box if they've seen a data center or something like that, right? But I'm absolutely convinced, and I see it in my kids already, that computing will be embedded all around us, that we will, and we already are seeing, that the notion of this computer being a discrete thing that we program is, we're going to have computers like that, but that computing is going to be embedded all around us. So Mark Weiser, who was at Xerox PARC, had this note, coined the phrase ubiquitous computing, where computing is all around us and it's restful, right? I love that phrase, restful computing, that it's not even there actively, it's just around us, and it's all just sort of calm, and it's just sort of there, right? So already, obviously, you know about smart vehicles, but even before we had smart vehicles, there was tons of computing and hundreds of thousands of lines of code in our cars, in our buildings, embedded around us in the environment. And so this is something I'll argue is already happening, and we're well on our way there. Now, I want to come back to the question about CyberHuman Systems here, and so think about HCI, and this is an area where this department has always been known nationally, and think about what does it mean to sort of interface with a computer in 2030, right? What does it mean for us as people when we're interacting with computation? And I want to say that at the University of Massachusetts, where I'm from, we always have a faculty retreat every year. And we go out and we argue, where is the future of computing this year? And we do it again the next year. And it doesn't change too much. But I would say about 4 or 5 years ago, we started having discussions in our faculty meeting, our faculty retreats, about this notion of the sort of the melding of human and computation together, and that needed to be an area that we really invested in. So if you think about assistive technologies, you think about smart prosthetics, you think about effective computing, the notion that the software that you interact with has a notion of your own, the emotions of the people or the individual that it's interacting with, and adapts accordingly. The mind-machine interface, the notion of silicon now embedded in neural pathways, the brain work that's going on. I think that of all of the changes that we're going to see between now and 2030, I think this may be the most profound. Okay, and so human-centered computing is something that certainly within IIS, but also even within CNS and CCF, the other divisions in CISE, is something that we're placing considerable emphasis on. And then finally, I don't know if we really have stovepiped applications or not, but as we move towards smart and connected communities, and you have what you might think of as sort of stovepiped applications, transportation, environment, public services, that all of these, when you start to be able to combine these informationally, you get sort of what's called a network effect, right? That the utility of combining things goes up as n squared rather than the sum of these individual things, and you get a lot of gains because of that. Okay, so I don't know. That look okay for one slide? I mean, I borrowed a lot from people, and it took a lot to sort of figure out in one slide what to explain to somebody about where computer science was going. Anybody see anything I left out? Yeah.
Comment. So I talked with CHS program managers. They agree with you that the most exciting work is in their division. They say that unlike the other portions of CISE, we are really badly funded.
Okay, so so the comment was that when you talk to somebody in CHS, Computer Human Systems inside CISE, they will say, yes, we are the most exciting program inside CISE, and they will say, and we are the least well-funded. I'm not sure they're the least well-funded, but it's true because of the proposal pressures that we've seen in IIS, for example, just broadly across machine learning and CHS, that those rates have been, those acceptance rates have been lower just because of the proposal pressure, and already this year we've taken some steps to sort of raise those up. So, making some central investments out of central funds that we have. So that sense is probably, that visceral sense is probably true. I'm not sure if it's has the lowest success rate, but it's, we're working on that. Yes?
So given you mentioned there are several things that keep you up at night, are you going to have time to speak about what initiatives you were trying to push forward, especially given the number of occasions you've gone down the hill to talk to folks there about policy changes?
Okay, yeah. So Fabian's comment was what keeps me up at night and what initiatives that I want to sort of push on. So let me make sure that I leave myself plenty of time to do that. I'm going to, because there's been a lot of discussion, which is great, I'm going to get to that. And I guess maybe what I'd like to do is I'd like to just sort of give you just a quick overview of a couple of things sort of in these different areas here, and then I do want to talk a bit about the future and where investments there might actually go. Okay, so you know, thinking about just a couple of areas to highlight: smart systems and robotics and the National Robotics Initiative. Of course, there's a computing aspect, there's the application aspect, there's the beyond HCI aspect of this. And so I mentioned smart and connected communities, smart and connected health. We have a program in that. Smart transportation, again, coming in, smart and connected communities. I will tell you that one thing before the election, the one thing that was certain was that both candidates felt very strongly about the investment in infrastructure. And sometimes people think infrastructure is all about concrete and steel, and it absolutely is, but there's cyber. Absolutely think about transportation and smart transportation, absolutely critical. So something that we're, an area just even within infrastructure and even in the near term that we're pushing hard on. Okay. I want to say a couple words just about experimental infrastructure, since this came up in a couple of conversations today. I had some interesting conversations with folks about GENI, the Global Environment for Networked Innovations, but what I really want to talk about is what's at the end right here, right? So we had, this was started almost 8 years ago. US Ignite, this is looking at gigabit applications. NSF Future Cloud, this is experimental research in cloud and end-to-end virtualization, sort of at national scale, at large scale. And then I wanted to talk a little bit about this, this power, just as there are a couple of interesting aspects about this. So power stands for Platforms for Advanced Wireless Research. And so this is all about, I don't know if you caught the announcement from the White House about the Advanced Wireless Initiative in July, but NSF is putting in, or CISE is putting in $50 million into this to build experimental test beds for wireless, and that's both at the sort of low-level technology level, but also going all the way up to applications, sort of at city scale. And I think in some sense, to get to your question, one of the things that's most interesting about this is that CISE has made a $50 million investment over 7 years in this. It's an important area. But actually, we've worked to form an industry collaborative that's actually putting in over $50 million together with CISE to create, this $100 million plus initiative on platforms for wireless research. So I like to bring this up simply as an example of being able to collaborate with industry, right? We talked about making the pie bigger and forging collaborations, outside of NSF and building partnerships with industry. I'll talk about some other partnerships in just a second, but to me, this is it's pretty exciting because it's actually the largest type of industry collaboration that we've had within, in the history of CISE. Okay. Let me just say a couple words about data science, since I know there are folks here who are interested in that. Foundational research, cyber infrastructure, collaborations and partnerships that we're doing there, and educational and workforce aspects there. So let me say here that we've got existing programs like big data, computational data, science and engineering, CDS&E. You can see some of the other collaborations here. I want to talk about, say just a couple words about a new program. I think the webinar for this is on Wednesday. This is called Tripods, Transdisciplinary Research, Transdisciplinary Research, the integration, in principles of data science. Sorry, I should remember that. It's a great acronym, but right. What this is this is a collaboration actually between the CISE Directorate and the MPS, Directorate in Math and Physical Sciences, to build a collaboration between mathematicians, statisticians, computer scientists, and computational scientists, really theoretical computer scientists, to work together on the foundations of data science. And the idea here, and this comes back to your question about timescales, again, also in sizes of grants. So when the director, or the assistant director for math and physical sciences, and I first started talking about this, we envisioned there are these things called math centers, which some of you may know about if you're more theoretically oriented. It's where, you know, there are 6 or 7 of these around the United States where mathematicians can sort of go, and they go on sabbatical, there are postdoc programs, and they do what mathematicians do. Oh, now I'm going to put myself in a box, and I'm going to say it publicly, and we're being recorded. Well, sorry, let me just say mathematicians come together to do research there, okay? And we sort of imagined that, oh, this would be really great to have mathematicians and computer scientists and statisticians come together at these places, and this is what we sort of envisioned this would be. And so we had a workshop, and we brought together mathematicians and statisticians and computer scientists, computational scientists, and, you know, so we said, okay, here's a workshop. Tell us what you think NSF should do. This is the way NSF works, right? NSF, for those of you who don't know, is sort of really special in that it's not top down and saying, oh, this is what the community is going to do. We really engage the community and listen to the community. And so we brought together this group of people, although honestly, I fully expected them to say, yeah, centers are a great idea. You know, fund 1 or 2 of these at this size. And what they came back with was they came back and they said, you know, let's not do centers. Maybe in the future we'll do centers. Let's do centerlets, or let's do something smaller. Now, they're not planning grants, not for just a bunch of faculty to sit around the table and talk to each other, but to actually fund research in different areas of theoretical data science. So that's what the proposal, you know, right now there's a request for proposals that's out. And let's try this for a few years. Let's fund these things at a larger number of these at a smaller level. Let's see where the points of collaboration are. Let's see where the stickiness is. And the only way to do that, to learn what really works and where the collaborations are, is by trying it, right? And so there'll be a larger number of these starts, and then eventually we imagine that these will turn into centers, and these centers will run for 5 years and then be extended for another 5 years beyond that. So that sort of talks about, you know, this is new sort of interdisciplinary collaborations, and that will, you know, if according to plan, would span 13 years, right? That you start out small, figure out what works, do 5 years again. And so, you know, that'll be, again, part of this portfolio of programs here. All right, so that's about fundamental research here. There's cyber infrastructure. So again, Fabian wanted to know things we're putting emphasis on, so, you know, we're making an investment there. In the theoretical foundations of data science, this has to do with cyber infrastructure, the data infrastructure building blocks you might have heard about. This has to do with education and workforce. And the one thing I wanted to say over here, collaborations and partnerships, has to do with the big data hubs and spokes. And so I know some folks here are involved in that. So let me simply say that this is another sort of new approach to programmatics within CISE. We fund basic research, but this is now also funding mechanisms to bring people together to collaborate in both hubs and spokes. And so there are 4 hubs around the United States. There's a southeast one that UNC is involved in. And then we just had a spokes competition where there are planning grants and spoke grants, which are a little bit more focused on a particular area, and made $12 million of investment there. Here's where they sort of fell out topically: smart cities, health, sharing reproducibility, environment, education. Okay, so I'm gonna, golly, I wanted to talk about augmenting human capabilities. I talked about that before a little bit in the brain. I'm gonna pass on that because I want to talk about education, and then I want to talk about the future. Okay, so not many people here heard about Computer Science for All. This is distressing. Okay, so Computer Science for All is a sorry, I almost said if you were to Google, if you were to search on Computer Science for All president address or something like that. So you know that going all the way back to FDR, the president has done a weekend address to the country, right? And so the weekend address to the country on the 30th of January of this year was all about computer science education. So our president talking about computer science education for 10 minutes. Right? That's how long these things last. I'm not going to show you the video here, but I don't know, I found it pretty inspiring that our president would talk about the importance of computer science for all. And for all means access in all high schools and equity of access among high schools. I mean, the sad fact is that right now, if you're in a high school in the United States, well, sorry, not a sad fact, the fact, sorry. I sort of wish I could rewind myself sometimes. The fact is, if you're in a high school now, you're 5 times more likely to have a high school football team than you are to have a computer science class in your high school, right? And so the goal of this is really to provide, as it says here, enable all students to have access to high quality computer science education in K through 12. This is something that builds on the CS10K program and the Broadening Participation in Computing Alliances that have been part of the CISE Directorate going back now 7 years plus. So really the work that, you know, having something like computer science for all really builds on things that have been going on within the CISE Directorate for quite some time. At NSF, we've committed $120 million over 5 years. This is between the CISE Directorate and the Education and Human Resources Directorate to fund CS for all. Okay, so this is all I was going to say about education. I would really, I don't know, I'll put a plug in to go listen to that. I wanted to show you this. This is a slide I got just like a little over a week ago, right? And after all of this work going back to from 2007, 2010, broadening participation, trying to fill the pipeline with more diverse sets of students coming in. What I want to show you here is maybe the first bit of maybe a leading indicator of good news. Okay, so what is this? This is showing the percentage of women. So this is, first of all, this is done by an organization called HARRY. Some of you who are students may have done, when you show up as freshmen on a lot of campuses, you do a survey, and it's all gathered at UCLA. This is plotting the percentage of women who are intended majors in physical sciences in green, in computer science, which is red, and engineering, which is blue. And so many of us have lived, I don't know, pick when you graduated. Here's 1984, when I graduated, right? It's been one downhill slide, and then we sort of bottomed out, and you see for actually the last 3 years, the percentage of women claiming, you know, stating that they want to major in computer science actually going up. So I just thought I'd pass on that piece of good news to you. All right, I'm going to skip past the NSF Big Ideas. Let me just say that what the big ideas are NSF proactively going forward. You can see the NSF Director, this is the headline from Science in May of this year. NSF Director unveils big ideas with an eye towards the next president and Congress. And so it's NSF sort of saying, hey, look, here are great things that NSF, and as you'll see in just a second, computer science can do for the country. So here's the list. There are some process ideas, and then there are some research ideas. I'll just say that there's harnessing data for 21st century science and engineering, shaping the human technology frontier. These obviously, as a matter of fact, all 6 of these have a very sort of strong size component. So again, just sort of thinking about the centrality of what we do. All right, so let me finish up. I want to talk about just a couple of future challenges here, and then I'll let people go. And really, any of you who are in the networking course who want to do a homework problem on the side, I'm really happy to do that, okay? I want to talk about partnerships, because I talked about industry a little bit. So I talked about this platform for advanced wireless research. And you know, this is all again about, are there new ways of having what can NSF do to help spawn new collaborations between industry, academia, and the federal government through the National Science Foundation. And so here's a bunch of activities. Many of these are new in 2016. So these are all a new solicitation on energy efficient computing that we're doing jointly with Semiconductor Research Consortium. We actually have 2 solicitations out that are joint with Intel, one with VMware, and let me just pick one of the Intel ones as an example. So here's what the model is for this, since I think this is a potentially very powerful idea. So NSF and Intel have issued a joint solicitation. If you're a PI and you say, oh, I want to submit this proposal in information-centric networking to NSF, you submit it, you can check a box saying, only NSF should see this, okay? And it gets reviewed through panel review like everything else. Alternatively, you could check a box and say, I want Intel also to be able to look at this. So Intel has 2 or 3 folks who sort of sit on the side of a panel and observe. They don't sort of actively participate, but they read the proposals, they read the reviews, and they listen to the discussion. And then NSF makes its decisions about what it will fund. And Intel has committed an equal amount of money to do a bilateral agreement between Intel and one of the university of someone who submitted one of these proposals to have an equal amount being provided by Intel. And so this is sort of a model that I'm hoping we're going to be able to scale. I mean, we've done it now with VMware, and there are some other discussions going on here. So anyway, I think that's I'm very hopeful that we can see sort of new forms of collaboration there. I talked about collaborations with other agencies like NIH, Cyber Physical Systems with DHS, DOT, NASA, and NIH. And so again, this notion of reaching out because computing is so central, and seeing that kind of collaboration with other industries and other agencies. Okay, and some international collaborations. I'm going to skip through those. Because the last thing I want to talk about, all right, this is the dean slide. Oh, it's an hour in, so I have to stop. All right, I picked the University of Massachusetts simply because I had the data, and this is where because I come from there, right? And is your undergraduate program director here? I know it used to be you, right? Okay, so this is Kevin before he became department chair, right? Superman, sort of standing up. There's this tidal wave of students who are coming in and saying, "Oh, we want to take computer science courses," and the faculty standing up and saying, "Okay, we can do it," right? So this is what these are the number of majors at the University of Massachusetts, and we became a college recently, and when we were talking to our chancellor and our provost about becoming a college, the increasing enrollments, but also the centrality of computer science sort of came into play there, and we have a really smart chancellor, right? And so even before I showed this data, we showed this data to the chancellor. The chancellor said, oh, you know what? I know computer science enrollments have gone up and down. Historically, I know what the periodicity is, and you're about to hit a cliff. No, we're not, and explained why it's different. I could go on and on about that, but I won't. And then he said to me, well, I know what you want me to think, right? You want me to look at that, and you want me to say, oh, look at that increase, and I should just be increasing my investments in computer science. And I said, no, that's not quite right, because of course an exponential fits that way better, right? And they didn't invest in us exponentially, but I think whether you think of it like that, or whether you think of it like that, and I mentioned the statistics before about the number of hires that are being advertised right now in computer science. I think we're really in an exceptional period of growth right now. Now that exceptional period of growth, I think, is going to have some consequences. And in particular, so this one's for Kevin, I think, right? Well, actually, the next one is. So this is getting to the question that came up earlier about, well, look, we've got an increasing size footprint. We see increasing tenure track. TT stands for tenure track faculty sizes. What happens with additional grant pressures? So that's, as I was talking about, trying to look for partnerships, arguing for increased funding, but looking for partnerships in industry with other directorates, and also with other agencies. And, you know, what's that going to mean in terms of grant pressures? We've talked about that 23% success rate. We've talked about other directorates having a lower success rate than that, okay? So if you've ever got any time and you want to read something, this is a very readable article. It talked about what happened when the National Institutes of Health basically doubled its research budget, and many more people came into the field, and research got hyper competitive. The average age when you get your first R01, that's sort of a basic NIH grant, the average age of a faculty member when they get their first R01 grant now is over 42 years old. And you know, I, being older than 42, like to think that, oh, you still got, you know, lots of good years beyond 42, but you've got a lot of good years before you get to 42, right? And so I wonder what kind of lessons there are for computer science given what's happened in biomed. All right, and this is, I'm going to stop after this slide. And this one's for Kevin or whoever your undergraduate is under. So, you know, so we've been thinking about, oh, look at all the computer science majors we have, right? And look at all the interest in our computer science programs. And I actually think it's going to be, well, in some ways worse, but in some ways way, way better, right? That there's a second wave of students who are coming in, right? And these are students who are coming in through computer science principles, the new AP exam. I didn't have a chance to really talk about that. This notion that computer science can be paired with other majors or minors across campus to create CS+X programs. And I think as we see more and more students coming up through these new high school courses, that we're going to see more and more students coming in. Some of the students will have taken the computer science A exam, you know, problem solving in Java. Other ones will have come through with this computer science principles and a broader exposure to computer science, the applications of computer science. And they're going to come to your, so I don't know anything about your undergraduate program, so I don't mean this personally to anybody here or at Duke or at NC State, right? But what happens to these students, this diverse group of students who've been coming up and they say, I'm here, I want to major in computer science, and what we say is, oh, well, then you should take CS1, CS2, discrete math, that's a great program, right? The way we've trained our undergraduates is great, I think, right? But there's this other class of students that are going to be coming that need other pathways through our major, and I'm going to argue that our deeply technical major, which is great, we don't want to change it. I mean, maybe we want to tweak it, but it's great, but that we're going to have this other class of students coming in who are going to really want other pathways through our major. Okay, so that's it. Thank you for, golly, time really flew. I'm really sorry. One of the things I've learned teaching for a long time is never to overstay your welcome, and I think I overstayed mine for at least 5 minutes. But let me finish up simply by saying it is an amazing time to be in computer science. There's so much happening. We are, I say this, I probably say this too many times. I said this to my chancellor at UMass too many times that, computing is central to a modern 21st century university where we all are. He once said to me, he said, everybody who comes and knocks on my door tells me what they're doing is central to this university. And I said, yeah, but it's really true in computer science, right? And, well, we're a college now, so maybe he believes it, I don't know. But, computing is everywhere. I hope you've gotten that sense. We interact with many different communities, with other directorates, with other disciplines, with other agencies, with industry, and so much is happening. It's rapidly expanding, and there's tremendous opportunity in sort of a very visceral sense that we've got to do things now. Okay, so with that, again, thank you for all the questions and comments, and I'm very happy to have more questions and comments, but I want to thank you all for staying, and thank you for inviting me down here. So thanks.
Let's see if there's any folks at the remote sites that want to ask a question first.
Somebody at a remote site, it'd be great if you could ask a question.
They may have had to beg off. Well, you can jump in anytime at a remote site.
Somebody going to a microphone? No?
We can take questions locally and they can jump in
Okay, all right.
as need be.
So any other comments or questions? Oh, call. All right, how do we answer the phone?
So local questions.
Oh, I was so hoping for a remote question.
Well, they'll jump in.
Okay,
Questions for Jim?
yes.
Hi, so I'm a relatively new faculty in machine learning and connecting
Okay.
image to vision and robotics. So as you said, this area hopefully is seeing a lot of growth, but then on the downside, how frequent is the redistribution inside NSF in terms of
Oh, okay.
not just my area, but any area seeing growth?
Right.
Is it like the reallocation of resources?
Right, so the question is reallocation of resources inside NSF. Let me simply say that we look at success rates and track them on a yearly basis. So when we start to see shifts like we're seeing now, we like to be very data driven, so we keep a very close eye on that. So I want to say sort of constant, but on a yearly basis.
And the second part to the question was, so you mentioned Intel and VMware,
Yep.
and some of these successful partnerships. So from the more machine learning
Right.
perspective, Google, Microsoft, Facebook research, are they interested in?
Yeah, so the comment is that if you looked at SRC and Intel and VMware, they tend to be a little more systems oriented, and what about Facebook and Google and other companies like that? So let me just say, those are companies that we all know about and would love to collaborate with, and there are ongoing discussions.
Thanks.
Was there somebody remote? Okay. Sorry, yeah.
So arguably, NSF reviews are more important than paper reviews.
Okay, yeah.
Good money. And in conference reviews, there are rebuttals, at least that I go to.
Yeah.
And NSF, at least in the program I submit, the reviewer can get away with saying anything.
Okay.
And often the reviews are done at the last minute. It's not as if conflict in there. So of course, every time you get declined, that's what you think. So
I know exactly how you feel.
I'm just curious whether there could be some rebuttal. So some way for the person, and that will I think make it also more efficient because people spend a long time on the panel trying to interpret what was said. So
Right.
if you could just answer saying, here on page 55, I say 2 and 2 is 4, and it's not 5.
Okay. So great. So there was a statement and a question. So the statement was that many conferences actually do what are called rebuttals. So you send in your paper, you get a set of reviews back, and you as an author get like a week or two to actually provide comments back to the referees, and then a final decision has been made. And so Priscilla's comment or question, I guess, was, what about this within NSF or within CISE? So actually, we did an experiment. We've just completed an experiment like that in CCF, where there was an opportunity for a rebuttal phase. And we're actually looking at the results of that, sort of as we speak. Let me comment though on what I take as the experience of what people have learned in conferences, because SIGCOM has done it, and I've been involved in that. And there was an ACM conference on conference and workshops. I don't know if you ever saw that, but it was getting together people who'd been program chairs and workshop chairs and said, what have we learned collectively? And so one of the questions that this group was asked to address was, were rebuttals actually worth the work, and did it lead to better outcomes? And if you look at that report, it's mixed at best, right? That do the rebuttals actually change what the decisions are? Not in a lot of cases. And it has to do with, is a rebuttal simply trying to reiterate and say a little bit louder what you were trying to say, or does it correct factual errors? And absolutely, to the extent that you can correct factual mistakes in reviews and stuff like that, they're incredibly valuable.
So, they did not change the verdict. The fact that they're going to be rebuttals probably made the reviewers more careful.
Right. So there could be an argument that the fact that there are rebuttals and that your rebuttals will, well, nothing's public, right? But that the fact that there just are rebuttals will make you a little bit more cautious. we'll see. So we're actually evaluating what happened in the CCF right now. Yes?
I just want to ask your opinion of computer science as a discipline moving forward. In particular, computer science is more pervasive, and I can see other departments and things sort of saying, we would like to add someone in our physics department,
Right.
our math department, or whatever that teaches the version of computer science that we want, that we think
Right.
is necessary for our major.
Right.
I see that as an increasing trend.
Right.
And to some extent, it's also addressing the fact that people are coming out of high school with some more computational knowledge they don't need.
Right.
And I'm wondering, in particular, if what above this trend is to move from a department toward the college model, where you can have a more multidisciplinary approach, or how do you see computer science evolving as a discipline? Is it going to go the path of math, where there are relatively few math majors, but everybody has to take something?
Right.
Or in some other model?
Okay, wow. That's at least an hour-long discussion, but I mean, it's a great question, right? So it's really about where does the discipline go? So the comment's been made, and it's absolutely true, right? That with more and more disciplines requiring computational fluency and capabilities, that other departments could teach that. In some cases, they are teaching that. And where do I see departments going? And honestly, I think that it's going to depend very much on the sort of individual academic ecosystem where you are, right? And so certainly at my universities, and I think a lot of universities, when you try to be outward facing, you want to collaborate with people. So it doesn't mean that everybody who ever teaches anything about computational thinking has to be a computer scientist, but I think computer scientists would want some input into that. And so it may be collaborations where, okay, it's being taught in the sociology department, but maybe it's being co-taught with a computer scientist, or maybe it goes back and forth. You mentioned math so some people call math the old horizontal, meaning that everybody across the university needs math, right? And computing being the new horizontal, right? It's not replacing math, because you absolutely need math, right? But I do think that you need computing sort of horizontally, and that it will be one of these new horizontals. And again, how that's taught is going to depend on what individual departments, because if your department says, I mean, let me not say you, if a department says, well, we want to do what we've always done and let somebody else do it, somebody else will do it, right? And that happened to many statistics departments around so I think statistics is even a better example than mathematics. And I think that's a discipline that by and large probably chose to not do so much teaching outside of its own discipline. But where that goes, I don't know. It's going to depend on your budget model. It could depend on a lot of very different things. Yes? Yeah? Mm-hmm.
So earlier when you had us do the thought experiment, right, thinking about where we'll be in 2030, looking back, seeing what would have to change,
Mm-hmm.
the biggest thing that came to me was policy and policy shaping.
Yeah.
And I'm just curious, right now, currently in your work, where is the resistance to the expansion of policy, or the shaping of it cross-culturally or transnationally?
Wow.
Where are you seeing that resistance come?
What a great question. So the question was, with respect to policy, where is there resistance to policy? And actually, I don't think there's resistance to policy. The question to me is how policy gets made. And if you think about some of the AI technologies and I had a couple of conversations here today about driverless cars, and who actually sets the policies for that, and what does that mean for all sorts of issues that surround the public responsibility for that, the legal responsibilities for that. How does that get said if you think about AI and any of a number of other application areas? One of the amazing things about being in Washington is that you meet so many interesting people. And so I was in a meeting about a week and a half ago where this issue of policy came up. I won't tell you where anyway, it was in DC, and there were a bunch of different federal agencies there, and there were a bunch of computer scientists there, right? About a third of the room was computer scientists. There was a state Supreme Court justice, there were some economic people there, and we were talking about exactly these kinds of policy issues. And I don't know if you followed I think it's either IJICAI or AAAI that had a, use of AI policy sort of manifesto that came out. The conference was in South America, and it was a bunch of computer scientists saying, here are what we consider, these are the things that we don't think we should be working on. And the question, the comment that was made to the computer scientists in the audience was that policy is not shouldn't be set by computer scientists, that it should be informed by computer scientists, but that how policies get set is a very complicated social and political process, and we absolutely need computer scientists in the room and in the discussion about it, but that it's a really much broader question than, for us as computer scientists and computer engineers to be saying, oh, this is what the policy should be, just because we create those systems. And I found that to be, a pretty interesting, a very interesting insight. Anyway, there's a computer scientist, Lori Craner, who's the chief technologist at the Federal Trade Commission right now. So she's a computer scientist from Carnegie Mellon, and she talks about the real need to have computer scientists in Washington for precisely to be able to inform the kinds of policy decisions that the FTC, Federal Trade Commission, for instance, has to make. So when you think about careers, it's not just careers in places like the companies we've been talking about here. There are careers in government, there's careers in policy, and that you can use the kinds of education you get here as an undergraduate or graduate student, or as, at some point in your career, spend some time in Washington, because the policy, that's where, that affects us all and is really important. So actually, I don't see a lot of pushback, except that the only pushback I've ever seen is that we should never think as computer scientists, because we create these systems, that we should embed a policy decision into it, that this is how it should or should not, or can or cannot be used. But great question.
Well, thank you all for coming. Let's
Okay,
Jim again.
thank you again. And I wasn't kidding about the 4:30.